as B over A. We can also define it as 1 minus B over A, but it doesn't matter. The main idea is that this compression ratio will always be above something. This something is the length of the sequence minus a constant number. So it cannot be compressed too much when the sequence grows up. Is it too complex here? I think I probably messed it up.
Should be R should be greater.
Yes, if we define it as B over A, this R will always be greater than the length minus a constant. If we can find this constant C, then we say this sequence is incompressible. However, one mathematician found that this sequence that follows this definition doesn't exist. So they tried to change the definition of compression. So finally, after some operations, finally they got another definition. But the main idea is you try to compress this sequence, and you cannot be compressed. Cannot be compressed too much when it's random sequence. The third approach is called unpredictability, which means this sequence can hardly be predicted. And I'm going to show you something about it in the next slide. So these are basically the three approaches. But there are severe problems in these approaches. The first one is those definitions are only suitable for infinite sequences. If you change that to finite sequences, none of them will work. For example, this measure periodic approach. So let's assume here is a sequence, infinite sequence, that follows the first definition. But if I define a function, if I already know this sequence, and I define a function to only extract these zeros, if this is finite, I can always find a function to only get the zeros. Then the result will contain 100% zero. Right? So these definitions are only for infinite sequences. Another bigger problem is if we already have a random sequence that satisfies any of these definitions, when we put a billion zeros at the beginning of the sequence, according to these definitions, the new sequence will still be random. Because 1 billion versus infinity is still 0. It doesn't play any role in the end of the analysis. So that makes it impossible to use these definitions. So the conclusion for this slide is that the infinite random sequence only exists as a fantasy in the dreams of the mathematicians. So let's be more realistic to consider finite sequences. But before that, I want to talk about this unpredictability much more. Before that, we want to know what this martingale betting system is, because it's a fundamental of this predictability. Do you know martingale? Yes? Have you tried using it? Okay. So martingale betting system is a very simple idea. That if you are betting with someone on zeros and ones, if you lose, then you double the amount of bet. If you win, then you use the basic amount, minimal amount of bet. Is it easy to understand? So the basic idea is that the first win will recover all previous losses, and with a profit that is equal to the minimum bet. So that was a strategy that was developed 20 years ago. And theoretically speaking, if you have a lot of money that you can afford these losses, then you will never lose by this martingale betting system. But the people who were using it actually all went bankrupt. And why is that? This method has no advantage over any other betting system. Let us do a very simple analysis. Let's calculate the expected profit per round. A round means if you win, this is counted as a round. If you lose, then you go on betting until you win. Okay? So, for example, you lost 3 times, and then you won. The 4 bettings are considered as one lot. If B is the minimum bet, and the Q is probability of losing in each round. If we use a fair coin system, it will be 50% as Q. And N is the number of bets the gambler can afford to lose. Then expected profit per round. Let me explain it a little more. So how can you lose? If you lose, that means you get N sequential losses, because N is the maximum number of bets you can lose. And this probability is very low. It's equal to Q to the power of N. This is a very small number. And otherwise you win with the profit of B, right? But if you calculate the expected outcome, it will be B multiplied by this thing. Let's assume the Q is 50%. We get 0. So if we play a fair game, the expected income will be 0. But in some of the games, the Q is slightly lower than 50%. Then you are going to lose money. The more money you have, the more money you are going to lose. Let me show you. This is a bankroll lot for 100 bets. In the beginning, you are accumulating money, but something happens here, so you lost a lot of money. But let's assume you have a large fortune, so you can recover. Then you go back. And finally, after 100 bets, you get this amount of money, around 50 units. In 1,000 bets, this is a big drop here. This is for 100,000 bets. And the extreme case will be 1 million bets. You are expected to gain some money if you have least money to lose. Right, that's a lot of money. So nobody wants to use it. Even though you are winning money, the return is very small compared to the money you have. If you already have this money, why do you go betting? Right? So never use this strategy. But how is this related to our predictability? In a unpredictability approach, they try to define that. Define the random sequence in that no matter how you choose this martingale function, you will never gain money from when the number of bets is approaching infinity. Understand this? So if we have a certain martingale function, actually it's called super martingale function. In martingale, when you lose, you add some money. So the compensation will be equal to your loss. But if you add more money to it, we call that super martingale. No matter which strategy you are using, no matter what parameters you are using, if your result is a random sequence, then you are not expected to gain money. That's their approach. Okay? But as I said, these random sequences don't exist. So to be more practical, we are using randomness tests. Here are some packages we can use. And they are used to measure your random sequences to see if they have a very good quality. But the fact that your random sequence passed this test doesn't mean that your random sequence is a perfect random sequence. But there are some tests. The earliest, one of the most famous tests was called die-hard tests in 1995. Then here are some other tests. If you want to test your random sequence, the latest one is called, and the most famous one is called test U01. Just feel free to use them because you can download them from online, from the website. So if your random number generator or pseudo-random number generator can pass this test, you will be perfect one. One of the earliest random number generator is the von Neumann method. I think we talked about von Neumann in the last lecture in Monte Carlo. He is very famous in computer science now. He developed this middle square method. Let's suppose our last input. We want to get 10 digits. Okay, we want to get a 10-digit decimal number as a random sequence. And if the last output is this one, as 10 digits, then we square it, and we get a much longer number. And we extract this middle part as the next output. So that was a very primitive PRNG, but it has severe problem, which is very short period of length. So you use it to generate numbers, and after a while, after a short while, you'll find it repeating itself. Then, the most widely used one is called a linear congruential generator, and I think it's still being used in a lot of libraries, like C++ libraries. Let me first introduce what congruential is. So this is a division, 23 divided by 5. Let's assume it's integer division. 23 divided by 5 is equal to 4, and we have a remainder of 3. And then we define a modulus operator. Then 23 mod 5 is equal to 3. Then we say 23 is congruent to 3 modulo 5. Because 23 mod 5 is equal to 3 mod 5. That equal to 3. So this attribute is called congruential. Okay? In linear congruential generator, we use a very simple function. The next output will be the last output multiplied by A and plus B and mod M. And its abbreviation is LCG. And typically we have the initial value of X, which is the seed that is used in random number generator. Let me give you a demo. So here is a series of numbers that are generated. If you change the seed, you are going to see different patterns, right? This is modulus, which is n. Modulus is this one. Modulus, mod n. If you change the modulus, you are going to see different patterns. And multiplier, and increment. So this is linear congruential. This is a small demo of it. Now, as you already see, this number is only for generating integers. But commonly speaking, when we use random number generators, we get a random number between 0 and 1. How do we do it? We can get it from a large number to a number between 0 and 1